Hey everybody. Today we're going to go through and we're going to begin to graph a more complex quadratic function. We're going to begin to graph changing parabolas. And what you can see up in the title for today, we're going to start graphing something that takes that form. So you'll notice I've just put an h and a k into that equation as placeholders for some missing values or some values that will be there. So what I want to do is I want to spend some time today examining, well, what is the effect of an h or a k? Again, just labels for values. And then I want to start to build up to us dealing with those properties of parabolas that we discussed earlier. Today, you're going to play around with Desmos a little bit, but we're also going to do some stuff by hand. I think it's really important for us to be able to work our way through. You'll see in the instruction a table of values. I'm not doing it to you to slow you down or for it to be a painstaking process, but I actually think that the act of using a table of values today is going to help you to understand why certain things happen. So, let's jump right in. You can see your first instruction on the set of axes below. I would like you to sketch, and I could say graph because it is on a grid. I want it to be as exact as possible. I want you to graph your base parabola. So let's use this as a gauge. Do we know y equals x squared well enough? If we do, this should take you somewhere between 10 and 15 seconds. Okay, pause the video now. Okay, we're back. So we should have had our vertex at 0, 0. We know we passed through 1, 1, and we know we passed through 2, 4. Those points are reflected on the other side of our axis of symmetry, and we can connect that with a smooth curve. We're getting a U and not a V, arrows on the end, and we should be good. We are going to go through and put a few different functions on that same set of axes. That means we're going to be required to label. So you could, if you wished, label that with an equation, the actual equation of the function. Or if you're looking for something, I don't know whether it's faster, but it might be better for space, we could now label that as equation 1 and simply use our universal form for an equation, a number was circled as our label. Okay, now what I would like you to do is I would like you to produce two different tables. I'm going to ask you over in the space, we're going to create a table for, and I'll label it as equation 2, y equals x squared plus 2, and I would like you to do a table for, let's call it equation 3. Y equals x squared minus 3. Okay, I'd like you to do a table for each. So, yes, I understand that this is going to be a little bit longer than what you would have liked. And you may have wanted to just use Desmos again to pattern some things out. As I mentioned earlier, I think it's going to be really useful for us to go through and examine what we're doing when we complete that table. So I want to pause it now. I want you to give it a chance to go through and complete those tables, and we'll see if we match up in the end. Okay? Pause the video now. Okay, we are back. So if I was to go through and complete for my table in 2, I might pick the same x values that we use to produce our base parabola. So maybe a -2, a -1, a 0, 1, and 2. And I'm going to do that for both parabolas. Not that it was needed, but those are some pretty easy values to sub in. Okay, if I go back to equation 2 in purple, if I sub in my -2, and I am just going to do this work down below. You did not have to do this. By all means, you should be able to do this in your head. But when I mentioned it might be useful for us, this is what I'm talking about. If I now calculate subbing in my -2 for my x, this act right here of squaring the -2 and now just adding on the 2 gets us to 6. There's my y value, and hopefully we match up. I want you to notice that every time you are completing your table of values, you're doing the same thing. You are squaring whatever your base is. So you are figuring out what your base parabola is. You're just squaring a number. And then we're just tacking on this addition of 2 in the end. So to confirm our table, -1 squared is 1, add on 2. 0 squared is 0, add on 2. 1 squared is 1, add on 2. 2 squared is 4, add on 2. Like you can even hear it in my voice, just the add on 2, add on 2. Okay, let's confirm our purple graph, equation 2. At -2, I'm all the way up at 6. At -1, I'm at 3. 0, I'm at 2. 1, I'm at 3. And 2, I'm at 6. You may notice that when you graph that function, you actually get the same shape as what we had before. If you notice, all my key points on my purple graph, they line up with my key points on my blue graph. If I'm looking at that sort of step method, then I would be examining how do I move. So I went over 1, up 1, over 1, up 3, and I noticed the same thing. Over 1, up 1, over 1, up 3. So I have the same shape on both of my parabolas. Okay, I can now work my way through my red table. If I caught up to you, this becomes an opportunity to pause the video and finish it off on your own. Otherwise, here we go. I'm going to do the same thing as what I did before. I'm going to show one substitution. I am subbing in my -2 for my x, and now I'm just subtracting off 3. So when I calculate that, I get the same value as my base function. There's my 4, but just take away the 3 every time. So I would get a y value of 1. And if I follow that pattern through, -1 squared is 1, subtract 3. 0 squared is 0, subtract 3. 1 squared is 1, subtract 3. 2 squared is 4, subtract 3. I'm hoping that this is droning on in your head, but I really want you to just hear the subtract 3. So what I'm doing, if I plot all those points, -2, 1, -1, -2, 0, -3, 1, -2, 2, 1, and I can connect those with a smooth curve. That now becomes equation 3, and you will notice the exact same thing happened. My shape did not change. I still have, if I look at my red graph, my over 1, up 1, over 1, up 3, the same shape. My graph just happens to be in a different location. So I really want to highlight what's been happening every single time we simply add on 2, subtract 3 from our base function. Okay, I am hoping that we matched up. I do not necessarily think you have any idea what we're doing yet, but I'm hoping we got to that point and we can see that our original blue graph has changed. Okay, let's try to sum it up a little bit through some extra patterning. Now is when I want you to hop onto Desmos. We've done enough tables. Now what I want you to do is to pattern out some things as fast as you can. So use Desmos now. Hop on and graph those following functions. All I want you to do, find the vertex. Make sure that you are on the vertex. So when you select where you think that change of direction is, make sure that that is the change of direction. You will notice that when you click on that value, it is a very special value for this function, and so the coordinates of that will likely stay. Okay, I want you to pause the video, go as fast as you can through those 4, and then I'm hoping that we can pattern some stuff out. Okay, pause it now. Okay, we're back. So I'm hoping that you found that you had a vertex at 0, 1 for that first one, a vertex at 0, -5 for the next one. You then had a vertex that gave you a decimal, 0, -2.5. And then you had a vertex that gave you 0 3/4. Decimals will show you that as a 0.75. Okay, I am hoping that you can see what the effect of adding or subtracting a value to x squared is. If you haven't noticed, that's what we've been doing every time. Can you look back up at the 4 equations I gave you to use on Desmos? There is my x squared. All we did was add something to it. There is my x squared. We subtracted something. There was my x squared. We subtracted something. There was my x squared. We added something. I could add ugly decimals. I can add integers, subtract the same. Does not matter. All we're doing is adding and subtracting to our x squared. What was the change in the graph? Now, I'm going to give you some terminology here. When a number is added or subtracted to y equals x squared, its graph is, and there's 2 words for that. A very formal word would be translated. There was a translation that took place. Now, translated starts to sound like another word that we would use. And so I'm not a big fan of it. The word that I would prefer to use, because it doesn't sound like anything else, we're not going to confuse it for anything else, would be the word shifted. When I add or subtract a value to y equals x squared, I shift my graph. Shift means, way down below, shape stays the same. And we reviewed that as we went through. I'm not changing the shape of my graph, I'm simply changing its location. Now what we need to make sure that we nail down is that they all moved in the same direction. You will notice that when I added or subtracted a value to x squared, my graph always moved up or down. So when I say its graph is translated or shifted, it is important for us to note vertically. It is a vertical shift. Notice that when I add something, my graph shifted up, and when I subtract something, my graph shifted down. That hopefully makes sense to you because all we were doing was adding or subtracting a value to our base function. So you're taking your normal parabola and you're adding something to its output. You're subtracting something to its output. And there we go. Okay, we've just covered our first shift. Nice. Okay, I want to change gears a little bit. Here we go. Now you'll see the instruction on problem 2. We're back to our good old grid, and I want you to do the same thing again. I want you to put on our base parabola. We should be nice and fast, 10 to 15 seconds. Pause the video now. Okay, we're back. We should be good. 0, 0, 1, 1, 2, 4. We're picking up the pace. Reflect them. Connect them with a smooth curve. Make sure it's a U, not a V. There is my base parabola. I'm going to call it equation 1 right now because I can kind of see where we're going. There we go. Okay, the second part of that instruction. We're going back to our table of values again. Again, I'm not trying to slow you down, but I think that there is something super important in the act we are about to do. I want you to use a table of values, and I'll keep kind of my colors the same. Let's go equation 2, and let's go equation 3. We are going to go through and produce our table. There's my good old table. There's my good old table, and I will match up with colors again. I'm going to go through and show one more long process of substitution. You do not need to do that. But again, I want us to see it should be pretty solid for us to be able to go through and experience those calculations. Okay, pause the video now. We'll come back and we'll see if our tables match up. Okay, pause it now. Okay, we are back. So I go through and I use maybe my same values that I have always used. And I'm going to go and make the substitution again of my -2. Down below, when I do that, I am now going to get -2 minus 2, square it. And I want you to notice something changed in what I'm doing. I'm no longer calculating my base parabola. I'm not. Because that -2 is happening before I square it. And the act of squaring is what produces my parabola. Look back up to my equation 1. It's this act of squaring which makes that parabola's shape occur. But now if you look down on my purple equation, I am not squaring that thing until I calculate the inside, which means I'm changing some stuff a little bit. Okay, what is the impact of that? Well, let's work our way through and let's see. Now I'm going to calculate the inside. That's a -4. I need to square that, 16. So -2 gets me up to 16. I can already see that's not going to be a point that I'm going to be able to plot. Work my way through and do the same process. I don't think I need to write it down anymore. I have to take -1 and now subtract 2. So there's a -3. Now square that, 9. Sub in 0. 0 minus 2 is -2. Square it is 4. Sub in a 1. 1 minus 2 is -1. Square it is 1. It's a kind of a sloppy one. Sub in a 2. 2 minus 2 is 0. Square that is 0. And I notice that I'm able to plot 3 of those points. So I'm going to go ahead and plot them. 0, 4, 1, 1, 2, 0. Now, if that is not enough for us, even though we can maybe see that -3, 9 puts me up here and -2, 16 puts me way up, then what I can do is obviously extend my table. If I make one more substitution, let's say I sub in the next integer, 3. Well, 3 minus 2 is 1, 1 squared is 1. As soon as I now get that green point, I should be good. I have points across from each other, which means I know where my axis of symmetry is, and I should be good then to reflect the points that I can see to be able to produce my parabola. There is my equation 2. Okay, I may have caught up to you a little bit. What I want you to do now, pause the video and work your way through equation 3. Okay, pause it now. Okay, we're back. So if I tackle the same thing, again, I'm going to do one substitution. I sub in my -2. Now I add 1. Notice I'm doing the same thing again. I am affecting my parabola before I create my parabola. I'm doing it before the squared. So when I make that calculation, I get a -1 squared. There is my 1. There we go. And I could work my way through relatively quickly. -1 plus 1 is 0. Square it. 0 plus 1 is 1. Square it. 1 plus 1 is 2. Square it. 2 plus 1 is 3. Square it. So again, you will notice that I'm doing my operation before my squared. Okay, what impact does that have? Well, I plot my points, -2, 1, -1, 0, 0, 1. I love that. I already have points across from each other. I have enough information. 1 to 4, and 2, 9 puts me off my grid. Well, because I see points across from each other, I know where my axis of symmetry is, so I can reflect that across, smooth curve, and there's equation 3. Okay, I want you to examine your blue graph, your base parabola, somehow became your purple graph by subtracting 2 before we squared. Your blue graph, your base parabola, then became your red graph by adding 1 before we squared. And this had an effect on my graph. I want you to start to look and see, well, what do you think adding or subtracting before we square it does? Okay, same thing as we did before. Let's jump into some patterning. We get an opportunity again to go through and use Desmos. So I want you to go ahead, use Desmos to graph those functions, find your vertex again. We should be good with this process. Pause the video now. Okay, we're back. So hopefully we went through and we did a little patterning and we were able to see that we got a vertex at 1, 0. You got a vertex at -4, 0. You then got a vertex when we subbed in an ugly decimal. Well, I guess not that ugly. -3.50. And you got a vertex at 1/2, 0. Or what would have likely shown as 0.5. Okay. I'm hoping we can see what has now happened. We are adding or subtracting 2x. Notice we are affecting our x now before we square it. So if you scan back up, you'll notice we went through and we subtracted 1 from x. We added 4 to x. We added 3 we subtracted 1/2. We are affecting x now. That had a different effect. Okay, what happened? Well, I'm hoping that we're good then, that we noticed that our graphs still moved. So there was still a translation. So it translated, and we should be good from our prior discussion. You could say that it shifted. But I'm hoping you recognized that we had something different. Shape stayed the same, but the graph moved in a different direction. And we should be good that that was horizontally. And so we should be okay then to notice that when we add or subtract something to the x, that our graph moves in a horizontal direction. It's moving left or right, not up or down. Okay, what I want to do now is I want to tie all this stuff together. You'll notice the 4 equations that I gave you now have things added or subtracted to it in a number of spots. You will also notice the last 2 equations. I've also put in a good old a value out in front. Let's see if there's some effect by that a value. Okay, I would like you to go back, and we'll save our time again. Let's use Desmos. I want you to type in the equations to those functions. I want you to find your vertex again, and we'll see if we match up. Okay, pause the video now. Okay, we're back. I'm hoping that we found that we had a vertex of 7, 12, and that was something that you predicted. At the very least, you can see, well, when I subtracted a 7 on the inside, that meant that my parabola moved to the right. When I added 12 to the end, that meant that my parabola shifted up. Now, I might argue to you, one of those changes was very predictable. I would argue the red. If we go and we add 12 to something, then that's going to shift it up. I'm affecting my output. However, we may not have taken the time to notice that the blue might seem a little backwards to us. If I see a -7 on the inside, I might think to myself, well, I'm subtracting 7. And horizontally, subtracting 7 should have been left. Like that takes me in that direction on my number line. And here's where I want to take a moment to make sure that we are good with something. So, again, the whole key is it's happening before we square it. So if I was to draw my number line, and it's a very crude number line, and I'll just put 0 down in there just so maybe we can have some sense. If my normal parabola has its vertex at 0, 0, I don't even care about my y-axis because my parabola is only moving horizontally based on the 7. Well, if my equation now tells me subtract 7 before I square it, then I hope that we can see that we are hurting the value of x before I square. I'm taking something away from x before I try to turn it into a parabola. Specifically, I'm subtracting 7 from it. Okay. Let me write that equation down one more time. If I am subtracting 7 from that x, then does it make sense that all of my x's have to be 7 bigger than what they used to be to get me back to my base parabola? Okay, let me give you an instance. For me to get that 0 on the inside, which matched up with our old vertex, I would now have to sub in an x value of 7. That gives me 7 minus 7. There's my 0. 0 squared is 0. So it's now an x value of 7 way out here that gets me my vertex. Because I'm subtracting from x, my x's need to be bigger than what they used to be. And where is bigger? Where is 7 more on my x-axis? It's to the right. And so I'm hoping, if I erase all that mess, that you can see that by me subtracting 7 on the inside, I actually go in the opposite direction. I need 7 bigger. Bigger is right. Okay, let's see if that pattern plays through. Take a look at the second one, or the one in the top right. I'm hoping we got a little confirmation that the y-coordinate of your vertex was -26, and you should have found that the x-coordinate of your vertex was -8.5. Okay, because I am adding something to my x before I square it, that means my x's all have to be less than what they used to be to get my base parabola. So by adding 8.5 to it, I actually move my parabola to the left. I have that opposite operation effect again. Okay, let's take a look at the bottom two. Really, the only reason I put those in was, as I mentioned, can we examine, does the a value do anything to our vertex? So hopefully as you worked your way through, you found that on the first one, your vertex was at 1, -9, and you should have found that it really didn't affect it. By putting that -1 on the inside, you saw your parabola's vertex move to the right, and the -9 on the outside shifted your parabola down. Do we see that same thing in our last parabola? I'm hoping that you came up with a vertex of -3, 14. the plus 3 on the inside, I'm adding 3, so my x's are 3 less, shifted to the left. And me adding 14 on the end, outside my squared, shifted my parabola up. Okay, I am hoping that we have that in terms of some patterning. So where does the title come in for today? Well, that's where if I write this down nice and big, I'm going to add in a component for us. That is not the exact title for today because I snuck that A in there again. I am hoping that we are good, that we recognize that A was our vertical stretch. I'm going to put just a little V out in front. I hope we're good on that vertical stretch. It stretched it because it determined our shape. If my A was negative, well then I could have also had a reflection, as what you found in that last parabola you used on Desmos. Today, we can now introduce that minus h. That h represents a horizontal shift. What happened on the inside of the squared affected my graph horizontally. And then what happened on the outside of my squared, that happened to be a vertical shift. So there are a lot of ways that we can affect that base parabola, and we've now examined all of them. Okay, what I want to do now moving forward, I want to see how well we can do at tying everything together. We're going to bring back in some of those properties we discussed at the beginning of this unit, the introduction to the parabola. Let's jump in. Okay, for problem 3, I have asked you to sketch, and I want to be very clear, this is by no means a formal sketch. We are going to go through and actually sketch quadratic functions, actually using many different methods. Really what I want to do is I just want to get down the most base picture so we have a sense of tying the properties together. We'll do the sketch in the end. What I want you to do, state all those listed properties. So if we were to look back up, there is my equation. Y equals 2 times x minus 3 squared minus 4. Honestly, I just plugged in a 2, a 3, and a 4. What I want us to do is to try to figure out, without using any pictures, like the easiest thing when you punch that into Desmos and see what you get. I don't want that. Let's examine the effect of the 2, the 3, and the 4 on that parabola, and we'll see if we can come up with those key features. Okay, I want you to try them on your own. This may be very, very difficult. Do not worry. We're going to walk you through them together. Okay, pause the video now. Okay, we're back. So, the first thing that I might highlight is that 2 out in front. We have spent some time examining what multiplying outside our function does, and we recognize that that is a vertical stretch by a factor of 2. Well, if I vertically stretch my parabola by a factor of 2, I am doubling everything vertically. That is going to affect my shape. It is not going to affect my direction of opening because it's positive. So my direction of opening will still be up. My shape then is going to be steeper. I can tell those two properties just from that 2. Okay, I'm going to argue to you, I can actually tell one other thing. I can tell whether my parabola has a max or a min or not because I know my direction of opening. If my parabola opens up, then it does not have a top. Those arrows go forever and ever, but it does have a bottom. So I know that that parabola has a minimum. It does not have a maximum. Okay, those 3 properties I can tell just from that 2. Okay, now let's tie some other things together. I'm going to link both the minus 3 and the minus 4 together. I don't like how thick that is. And now I just went and erased my 2 as well. So all I'm going to do is I'm going to try to shrink my pencil a little bit here. I'm going to link that minus 3 and that minus 4 because they do have the same effect on our graph. They shift it. They just happen to shift it in different directions. Why am I linking those? Well, if I went over and I just did a quick sketch on my parabola, or on my set of axes, then my quick sketch of my base parabola would look like the orange. Y equals x squared. Like if I even wanted to be more particular, that red is now going to make that graph steeper. That's y equals 2x squared. There's my vertical stretch by a factor of 2. Okay, what does the minus 3 and the minus 4 do? Well, the minus 3 on the inside says I'm subtracting 3 from my x's, therefore my x's have to be 3 bigger. So I'm shifting my graph to the right. That means my vertex is now moving over to 3. But then at the same time, we can see that minus 4 on the end, and I know that that minus 4 is a vertical shift. It is going to shift my graph down. So that means that my vertex isn't at that purple point, but it's actually down here somewhere. It's at 3, negative 4. Those two shifts give me the location of my vertex. Okay, I told you we were going to produce our picture in the end, so I want to get rid of all of that stuff. But you can see my purple has given me my vertex. Okay, well, what does that now tell me? Well, if I know my vertex, then I know my axis of symmetry. My axis of symmetry is the vertical line that makes one side of my parabola the mirror image of the other. So that line, since it's vertical, has to be x equals, and it has to pass through the vertex to make it my reflection line. There we go. Okay, now that I know my vertex, that it's at 3, negative 4, I know my max or min value. I already know that I have a minimum because of my direction of opening. But now I actually know the value. My parabola will never go below negative 4. If you can look back up into my equation, remember the y value is always the value of my function. So the minimum value of that function has to be at my vertex. That one might be a little confusing. When we tie in our picture, I think that that's going to make everything gel. Okay, domain and range. Well, I'm going to argue to you, your domain is one of those ones that should have been pretty automatic. We should be good that x can be anything. My range now. This is one where I think the picture's going to really help, but I'm hoping we're good that because I know my minimum value or my vertex, that I'm good that y has negative 4 as that key value. The part that actually helps me with that is my red, my a value. That's what tells me I have to be greater than or equal to that value. Okay, if we were able to work our way through and come up with all of those properties, I'm telling you, you are doing outstanding. Outstanding. But that should have been a very difficult process. Okay, what I want to do is I want to go through and do what we started before and work through those transformations. If I was to go through and put back on my base parabola, okay, there's my rough sketch, y equals x squared. I now have to make that parabola steeper. I affect its shape. I have to affect its shape before I shift it because multiplication comes before add or subtract in bed mass. I have to follow my order of operations. Now I have my graph in the correct shape. Now I need to move it. I need to shift the entire graph to the right 3 and down 4. So if I shift it to the right 3 and down 4, my vertex is now off the origin. So I get the red graph shape, and I'll do my best to try to draw the shape. Though I don't know, that's pretty close. That is now my sketch. As I said, very, very crude, not formal whatsoever. We'll go through that process later. But because my vertex is off of the origin, I'm going to need to label it. So there is, as I said, a crude sketch of that parabola, by no means accurate, but it gives me an idea. What I want you to do is just take a moment. I'm going to go through item by item so we can see all of those properties represented on our picture. The only thing I'm going to do, I'm going to get rid of the red and the orange parabolas. I don't want us to be confused by anything that is there that's not really a part of that parabola. So if I kind of extend it, clean it up a little bit, there's my sketch. Okay, let's take a look at all the properties. So take a look, direction of opening, we should be good on up. You notice the vertex at 3, -4. My axis of symmetry, which is never part of my sketch, is that vertical line that is going to go through, that vertical line, and I just lost part of my parabola there. There we go. My vertical line that goes through the vertex. There we go. You will notice that makes one side the mirror image of the other. The equation of that line would be x = 3. That parabola has a minimum value. It hits its minimum at this bottom. The minimum value is the value of the function. Notice that parabola never goes below -4. It's impossible for that parabola to have a y value of -5, let's say. The domain, the parabola keeps getting wider and wider as we extend. X can be anything. The range for that, all of your y values have to be greater than, you should now be able to see why we have to say greater than, because the direction of opening is up, or equal to your vertex. And it is the value of the function at your vertex, that -4. My graph is steeper. That is really hard to tell on my sketch because I have no other points labeled. That's the key to us doing a formal sketch a little later. Okay, there we go. We were able to state all those properties. Okay, I by no means think that this is automatic for you now, but I do think it would be very, very helpful for us to try one more. Here we go. Okay, I would like you to try the same thing. I would like you to go through and try to find all of those properties for your parabola without using a picture. And then we'll come together in the end and we'll see how well we're doing. Okay, pause the video now. Okay, we're back. I'm going to do the same thing. I'm just going to go in the opposite direction. I can see that I'm going to have to shift my parabola to the left 1, and I'm going to have to shift it down 5. So I'm going to just get rid of that circle. That's going to make my vertex -1, -5. Okay, what does that mean? Well, it means that I have a max or min value at -5. Because I haven't considered which direction my parabola opens, I don't know whether that's a max or a min yet. The default, I'm good that x has to be anything. I know that for all parabolas. I do know that when I find my range, it's y, and it relates to -5. I just don't know whether that's greater than or equal to or less than or equal to. My axis of symmetry, I skipped over that one. I can go back and fill that in. Make sure you give me the equation of the line, x = -1. And there is everything that I can find based on my shifts. The shift left, the shift down. Okay, now I'm going to examine what that negative 1/2 does. Well, to do that, I'm going to actually break it into its parts. I'm going to deal with the negative first. Because I see a negative a value out there, I know that my parabola has been shifted across my x-axis. And that is going to change my base parabola from opening up to opening down. What impact does that have? Well, that tells me that I have a maximum to my parabola. Off on the right, I'm just going to put on a quick sketch. My parabola opening down means I have no bottom. Those arrows mean forever, but I do have a top. So there is a maximum value. Now that also tells me that my y values have to be less than or equal to, since my parabola is opening down. Okay, I want to deal with that 1/2 part now. Since my stretch factor, my vertical stretch, is by a factor of 1/2, that is going to change my shape. Since it is less than 1, that is going to make it flatter. Okay, there are all my properties. I would love it if we matched up. If we did, I think you're ahead of the game. Now let's go through that sketching, crude sketching process again. My normal parabola would be there. If I affect its shape, I now have to reflect it across the x-axis, so I have the same shape. That would be my negative x squared. But now I need to make it flatter. All of my y values become a half of what they used to be. There is my y equals negative 1/2 x squared. Now what I need to do is do the purple, which is shift that parabola to the left 1 and down 5, which is going to make my vertex, I don't know, somewhere around there, let's say. Okay, if I was to go through and now complete a crude sketch, it might look something like this. There is my vertex at -1, -5. I have a flatter parabola than normal, and I should get confirmation on all of my properties. Okay, as I said, if you were able to get down to that and you felt confident in it, that is outstanding. I think we're doing great. Okay, like normal, your job, jump in and get some practice. Okay, best of luck.